is to show how psychologists and neuroscientists study consciousness, the way I talked about it this morning. And I'll show a short movie to illustrate something about brain, because it's really important to understand the subtlety, not like the subtle mind, but the subtlety of the brain. It's really very, very, very complex. And every time we look, we see more and more and more complexity. Did you see something there?
Some color, yes.
Did you see anything else besides color? Let's do that again. So why don't you all look at this picture and tell me what you see.
Yeah. So there were a couple of spots of colors.
Color, but nothing else.
And there were some edges to these spots.
Okay. Now, let's look at here. What do you see here? Let me do this again. Look very carefully. What do you see here?
No, it's difficult.
All right. Now look at here.
There's a face.
All right, so in the previous 3 movies, there was always this face present. The face was always there. So we can go back again. So now maybe now you'll see it. Do some people see a face here in this?
Yeah, I saw the eyes.
But here all see it.
He's only saying that maybe ladies' eyes are sharper. Did you see?
I saw it, yes. But I knew what he was going to show, so I
And there are conditions, yeah.
With training, you can see this better. So the point here, in all 3 movies, there was always this face there, but it was masked. What we mean by that, in the first and the second movie, just before the picture, there were these colors. Then there was a face, an image of the face, and then again followed immediately afterwards with these color splotches. And so in the brain, this gets mixed up together, and all you see are the colors, but you don't see the face. Although the face is clearly present, it's in all 3 movies, it's exactly 33 milliseconds, a 30th of a second present in all 3 movies. So now what we can do, we can put you, for example, Your Holiness, in a magnetic scanner, and we can see, is a part of your brain active when the face is present, even though you yourself did not see it. So we can ask, where are the parts of the brain that respond to when you consciously see the face, compared to the parts of the brain that respond when you don't see the face, but the face was still present. So we can track the footprints of consciousness in the brain, because some parts of the brain respond just to the image on the eye, but some parts of the brain will only respond when you actually consciously see the face. And so that part of the brain is much more closely related to consciousness. So here is a technique that Richie Davidson is using now in his lab to study the unconscious. So we project different pictures in your left and your right eye. So your left eye will only see the angry face. Your right eye will see these changing color squares. And what you will see for a minute or two is only the color. So what you'll see is only these changing colors. Unless you blink with the right eye, then you will immediately see the angry face. But if you keep both eyes open, you will not see the angry face, even though it's present in your eye.
So there is a sort of a partition here that separates.
Yes, and it's a partition, and you see one eye here and the other eye there.
Yeah, so it's near. Yeah, the object is close.
Yes, I mean here we have to bring it here.
Let in.
Yes, yes. So biologists have done, psychologists have done this experiment, just to show you one out of many. So what they do, they put in one eye, they put a picture of a naked lady or naked man. but then they hide, in the other eye, they hide it using these rapidly colors. So what you see, if I ask you, Your Holiness, what do you see? You don't say, oh, I see a naked lady or I see a naked man. You just see changing colors.
Then, Christoph?
But then you want to find out whether people are attending to the naked lady or to the naked man, maybe. And so to test that, what you do, you flash on. Can you see this? On the rightmost image, there's a little grating, and it's tilted. It's either in the left side or on the right side.
Yeah.
And it's tilted a little bit to the left or a little bit to the right. And your task is, Your Holiness, to tell me, the experimentalist, is it tilted to the left or is it tilted to the right?
Yeah, it's on the right, yeah.
Yeah, he's tilted to the right. And then I test, are you better on the side of the invisible naked person? Or is your performance worse on the side of the... See, here on the left side was the invisible naked lady. Or are you better doing this task on the other side?
And then?
So you look but don't see. You look at the lady but you don't see. And it turns out if you're a man, if Your Holiness does it, you are doing better if this grating is in front of the invisible naked lady. And you do worse if it's behind the invisible naked man. Like your attention doesn't like to go when there's an invisible naked man, but is attracted to invisible naked lady. And for women, it's the opposite. Well,
Solon's is talking about maybe it has to do with attractiveness as well.
well, yes, it will. It will, how attractive it is. But so using this experiment, you can show that your brain can attend to things even though you don't see them consciously. All I see is colors, these changing colors. Yet underneath is an invisible naked man or invisible naked woman, and depending on whether it's a man or woman, I will be attracted to it or I will be repelled from it. So this is how we test the unconscious. Not using Freud and psychoanalysis, but using modern tools to go underneath the light of consciousness, underneath the can of consciousness, to probe the unconscious brain and the unconscious mind, using techniques like this. All right, so we've learned through 150 years of psychology that there are many things inside your brain that are very complex that we don't have conscious access to. The way we move our bodies, the way we, any routine, tying your knots on your shoes, shaving, dressing, playing tennis, doing video game, doing computer typing that we do. We can do this very rapidly, but we do it unconsciously. And you can show experimentally that if I become conscious, okay, now I want to do the F, or now I want to do the G, I become more slow. The best thing is just you do it automatically.
But that's due to habituation.
Yes,
Yeah.
exactly.
Even though if you don't pay conscious attention, you can perform the task.
And you can perform it better
yeah.
than if you pay attention. But even things like speaking, it's very complex, but I don't have access to the underlying mechanism in my brain that produces this speech.
So Solness is wondering whether it's also a function of being able to apply meta-level attention, like kind of a monitoring processes.
For certain things, I think if you pay high-level attention, you train yourself, you can gain access. But for example, nobody's ever demonstrated that you can gain. There are parts of the brain that do not see the world in color, that see the world in black and white, like a black and white television. Yet nobody has ever shown any evidence that you can train yourself to only see the world in black and white. You don't have access to that part of the brain. You always see it in color, unless you're colorblind. But I see the world in color. I cannot say, okay, now I want to see the world just in gray. So certain things I think forever inaccessible to consciousness, while other things may not be with proper training. And I think he's going to say something later on to counter. And of course, 100 years of psychology and of Sigmund Freud has shown us there are many, many things. If I in an emotion, strong emotions, when I love and when I hate, I don't know why really I love or why I hate, and I have no access to the parts of my brain, the amygdala, for example, that give rise to strong emotions. I can go to a psychoanalyst, I can talk about it, I can think about it, but ultimately I don't have access to those parts of the brain that give rise to these very powerful emotions that govern the lives of some people. There's a lot of things that go on in the catacombs of the brain that totally escape consciousness. A few things are made conscious, and the question for us as neuroscientists is always, where's the difference between the things that are conscious and the things that are not conscious? So you can call these zombie systems. This is a rare creature. It comes from Belgium, and it's a zombie. It's a zombie. It's a figure of speech. There are many zombie systems inside our brain that act very complicated, very purposeful, but that bypass consciousness. And the question is, where's the difference at the level of the brain? So what neuroscientists are doing now over the last 20 years are taking those behaviors and going down to the level of individual nerve cells. And this is what I wanted to show in the last 10 minutes. Because we can now access individual nerve cells. And it's really the atoms are the basic elements of matter. Right? If I want to explain this, I need to know about carbon atoms and iron atoms and copper ions. We believe to understand the mind, we need to know about the atoms of the mind, of consciousness, and those we think are nerve cells. So I'm going to show you a beautiful movie here. It's not my movie. It's just a 2-minute demonstration, a dive into the brain of a mouse, which is roughly 1,000 times smaller than our brain, but it's very similar. And the nerve cells are very similar to human cells. They're a little bit smaller. And just to show you the complexity of the brain. Okay, so we'll have it without sound. We need to proceed. So it's a part of the brain called the hippocampus that we know is very closely involved in memories. And it's a subpart of the hippocampus called the dental gyrus, where new nerve cells are generated. And what this shows is the process of plasticity, of how things change. So it focuses in here. You can begin to see the structure is tiny. It's like this. It's a sliver. It's tiny, tiny, and we're zooming into it. And we're going to get very close and see the individual nerve cells. And here you see the electrical activity that Tanya mentioned yesterday, or that Wendy mentioned in the first day. The electrical spikes, they're called, these electrical pulses. Here you can begin to see the individual neuron, and this mouse is thinking, is maybe remembering something. You can see the electrical activity in all these neurons. And now we're focusing on one nerve cell in particular. This nerve cell is smaller than a piece of human hair. Human hair is roughly 4 times thicker than this particular cell.
Hair. Mm-hmm.
And it's a very delicate lace, a very delicate structure that we're focusing on. This is the dendritic tree, the input, where it gets input from other neurons. The green is a wiring from other neurons that go into this. And here you can see synapses, and they move about like little tentacles. They're very dynamic. The brain is dynamic, as we learned yesterday.
No.
And the green is an input wire, and the purple is the neuron we're looking at, and now it makes a connection. It's a little bit like a kiss. So a synapse is created. A synapse is a connection point between 2 neurons, and we think this is where memory is encoded. And now it sends electrical impulses from the green neuron into the purple neuron. The neuron will fire. And we think this is the process that occurs in strengthening a memory and recalling a memory. If we're going to recall anything about the thing today, it's because this process happens in our brain. Except in our brains, there are 100 billion of them, compared to 100 million or 50 million in the mouse brain. Now let me show you in the last movie. So here we just show again, these are microelectrodes, so the way we listen to all of this, because we can listen to these electrical activity inside the brain. And there is this lady at my university, Doris Sau, and she records here from one cell, and I'd like you to listen what it sounds like, and you can tell me what the cell likes. Okay, here we need sound. So the animal is being shown this picture while we so the animal, it's a monkey, looks at these pictures while we're recording from one neuron. And you can hear the neuron fire, these electrical pulses. Drp, drp. So what do you think this neuron responds to? What do you think this neuron fires to out of all these images?
I suppose food.
Well, so the animal's being shown different pictures of people, of faces, of food, of clocks, but the nerve cell only responds to certain things, right? And the question is, what does this neuron respond to? There it fired. There it fired. So the neuron really responds to faces. You can hear it, the faces again.
So how the scientist is registering this sound in a monitor?
Yeah, so you put in these electrodes, so Dorisau puts in these pieces of electrode and then amplifies and places sound through a loudspeaker.
Oh. This is a monkey, yeah?
This is a monkey.
Beautiful.
But we've done similar experiments in a human, in a patient, and it's very similar.
But these are lab monkeys, though.
Yes, these are not wild
who are
monkeys.
familiar with human beings.
Correct.
Yeah.
Correct.
So what about if you showed image of another monkey? Probably we will see a lot more neurons firing.
Yes,
Yeah.
yes,
Risha.
because
Yeah.
that's what they're used to. Yes.
Tavaresha.
Also in humans, if we are familiar with the person, the neurons will fire, these neurons will fire stronger.
Risha.
But the point is, we think that consciousness arises out of these sorts of interaction of billions of neurons in the brain. And this is how we think right now consciousness arises out of activity, biochemical activity of this sort in the brain. Thank you, Your Holiness.
So in some sense, His Holiness is saying that there is this proverbial question of between the chicken and egg, which came first. So the question is
consciousness of mind, then effect neuron, or first neuron movement.
because in order for the conscious experience to occur, if the causality is only one direction, then a lot of the functions can be done simply by the neuronal processes. Why is there the need for seeing the face?
After seeing,
We
then
do not
this
know.
neuron
Yeah.
activities start.
Right.
So consciousness first.
So His Holiness is saying that even in this experimental design, it presupposes the monkey to see the images first.
No, it's simultaneously that we think. No, we think it's together. Consciousness, the first person perspective is I see. The third person description is my neurons fire. We think it's this, you have one coin and one side is my experiences as subject. The other side is neurons fire. And you need both. You need the neurons firing, they give rise to conscious experience.
Okay?
Good.
All right.
Okay.
Please stay there for a moment. Rajesh, walk behind.
You want to go?
Great.
It's a great honor for me to be here. Your wonderful description at the beginning of this meeting about how you're bringing science to the Dharma reminded me of a very beautiful dialogue that took place about 100 years ago, but by letter rather than in person, between Gandhiji and Tagore, where Gandhiji actually said that he wanted to open the windows of his house to the winds of the world, but he didn't want to be swept off his feet. And so of course, that dialogue and that importance of bringing in modern influences is as much a challenge that we Indians have faced as I'm sure Tibetans are facing now. And your introduction about coming back to Drepung Monastery and how it is Tibet's Nalanda also reminded me that some of the great acharyas of Nalanda, Nagarjuna, Dignaga, they were South Indians from around this area. And I'm also a South Indian from around this area. So it feels like coming back home for me as well. And my goal today is to do something what I might call mathematical madhyamika, right? So the idea being that madhyamika gives us a way to understand phenomena as phenomena without going into mechanisms. And I believe that mathematics, from the time of Newton onward, also gives us a way to get to the essence of a phenomenon without necessarily implicating mechanisms and other, you might say, Cartesian approaches to science into its theorizing. So what I'm going to do is to introduce you to some of these mathematical approaches to the mind in the context of consciousness, but primarily in relation to the acquisition and origins of knowledge, which is such a beautiful and deep topic in the pramana accounts in the Indian traditions as well. And as you know, in the pramana theories, knowledge or a pramana, an instrument of knowledge, produces knowledge when certain conditions are met, which are usually phrased as contact between the organ and the object. But Nagarjuna and other skeptics might respond that if the pramana produces a knowledge and it verifies that knowledge, what is the support of the pramana itself? Right? And that's the deep criticism of pramana theories from within the Buddhist traditions themselves, that who is the verifier of the instrument that produces knowledge? And this is a topic which, of course, the Indian philosophers and the Tibetan philosophers have spent centuries. But what I'm going to introduce to you is a way of looking at this problem that actually comes from the Western tradition, right? And in particular, Descartes, who has been mentioned many times in this conference, had a beautiful idea. He said that, because he was also trying to be a skeptic, he was saying that I can doubt everything, but what I cannot doubt is the experience itself. So for example, you can mistake a snake for a rope, and you might see a snake when you actually have a rope in front of you, but you can't say that I didn't see the snake. The actual experience of the snake is not open to doubt. So that idea that your mind has some internal structures which produce experience, and that structure experience is the idea that lends itself to mathematical inquiry and becomes this beautiful topic in the cognitive sciences, which has affected so many of the disciplines that we study today. So I'll introduce the formal question first. So the idea is that we see the world around us as a stable entity, right? So when you move your eyes, when you move your head, it doesn't seem like the whole world is spinning. When we use words, they have stable reference. So I say computer and it's in front of me. So somehow it appears as if that the world has this stability that allows us to use words, percepts, to make reference to objects and events and people in the world. And yet, the input, the sensory input to our visual, auditory, conceptual systems is very fleeting. It changes every single saccade. So how is it that you get this stable world, which is the world of that you produce through knowledge, out of such fleeting, unstable inputs? And that is fundamentally a mathematical problem, even though it might be expressed in the brain, maybe, or not. It may be expressed in robots, it might be expressed in the internet, we don't know. But the fact is that it's a mathematical problem. And mathematics allows us to phrase this problem precisely and give it and come up with conclusions that tell us beautiful things about the nature of our minds. So how do we go about doing that? So let me give you a sentence. So I might say, Rajesh is in Drepung. Then I might say, Rajesh, who's from Bangalore, is in Drepung. I might say, Rajesh, who's from Bangalore and who studied in America, is in Drepung. Rajesh, who's from Bangalore, who studied in America and is wearing a blue shirt, is in Drepung. As you can see, at least if you're a native English speaker, and if you're getting a Tibetan translation, all of these are grammatical sentences, and you don't have any problem understanding their meaning. And yet, I can guarantee you that it's almost certain that it's the first time in the history of the universe that these sentences were uttered, right? So how is it that something that you never experienced before, which is complex and involved, and nevertheless is accessible to your mind? And the answer to that is potentially the most important theoretical invention of the 20th century, which was applied to the study of the mind, which is the computer. Right? But not the computer as a physical device, but computation as a theoretical mathematical tool to understand how the mind works. And the reason is that, and this is due to the work of a linguist named Chomsky, that potentially your mind has the capacity to understand an infinite number of sentences which have never been heard before, and you're hearing them for the first time, but your mind is a finite device. So how is it possible for a finite entity to understand an infinite number of potential experiences? And there's a technical answer to that question, and it comes through something called recursion. But the idea, nevertheless, is that infinity, right? So infinity, which is a fundamental mathematical concept, makes its appearance in our understanding of the mind. And what you could argue the computational approach to the mind says is, instead of trying to understand the mind one experience at a time, let's try to understand all experiences. So let's try to understand a device, a computational device, which would generate every possible experience. And if we can give that a mathematical treatment, you're all set. Because what that's saying is that that computational device which can generate an infinite number of experiences, whether that is perceptual, whether that is linguistic, whether that is auditory, emotional, is the heart of the mind. That's at least what the computationalists think. So how would that work? The one possible answer is through what's called a grammar. So the idea is that there is some grammar-generating entity. Incidentally, Panini, the great Indian linguist, had this idea 2,500 or so years ago that the rules of grammar can potentially be formalized. But Chomsky and others took that a lot further, and they said that there are grammatical principles that can potentially generate every single human language. So that grammar is an innate faculty of the human mind, so that we all are born with this grammatical capacity, and unless you are a feral child, like what Richie mentioned a couple of days ago, you will grow up to be a speaker of some language that you were exposed to. The same thing can be applied to perception. So the idea is that perception, when you walk around a room, it's not as if suddenly you see holes in your vision, like a computer that says, I'm sorry, I can't recognize what's in front of me. No, you see this complete field, and the claim is that your visual system computationally is capable of recovering the shape and structure and size of every possible entity. And of course, you haven't seen most entities. Till 20 or 50 years ago, there were no laptops, and yet we don't have any problem recognizing laptops when we see them. So how is it that our visual system is capable of recognizing an infinite number of different entities without exposure to them. And the answer in all of these cases, the Cartesian answer actually, is that this must be an intrinsic capacity of our mind. That our mind has this intrinsic capacity to be capable of seeing 3D objects, to be capable of hearing sound as speech, to be able to extract grammar, do all of these things. So this is a very, very powerful idea. For purely mathematical grounds, you're saying that our mind is one way and not some other way. So it's a way to discover properties of how the mind works without actually going into brains, so by just looking at phenomena.
So am I right in summarizing to His Holiness that the main point that the computational model is bringing on the table is the kind of the benefits of looking at the problem of consciousness and knowledge in more functionalistic terms, rather than trying to ask the question, what is the substrate? What is the material stuff that makes these things possible?
Exactly. So to give you an idea, let's take a calculator, right? I mean, a calculator can be done with an abacus. It can be done on a laptop. Now all our mobile phones and everything have calculators. But the fact is that all of them are doing addition, subtraction, multiplication, and it doesn't depend necessarily on the material substrate on which that calculation is done, right? And this is a profound idea, and it's tied to what Christoph mentioned earlier today, that if you can give an informational characterization of mental activity or brain activity, then anything that has that characterization potentially also has consciousness or other things. And people like us who grow up with robots and other things that you dream about at MIT and other places, it's a very, perhaps a romantic view of what computation can do. I'm not necessarily saying that is the real truth, but it's a significant advance in understanding precisely how minds work. Okay? So, having said that, there are many reasons why we don't believe in that kind of computation anymore. And let me give you two reasons. See, computation is precise and logical. Unfortunately, logic doesn't seem to work when you really look at human conceptual and perceptual phenomena closely. So to give you a very perhaps topically relevant example, let's take the concept bachelor. Right? You might say bachelors are unmarried men. So most people then in this room would be bachelors. But it doesn't strike me that we would call most monks in this room bachelors, because somehow their bachelorhood is not tied to choice, but to the religious principles that make you into unmarried men. And so therefore, you could argue that then a bachelor is an unmarried man who is unmarried by choice. But then somebody could say, and some of us might do, who are married, might say, oh, my wife is away for 2 weeks, I can be a bachelor again. Right? And so definitions and you could argue mathematical constructs don't seem to capture exactly how concepts behave. So there's an alternative account now, and which comes from the work of people like Francisco and others, George Lakoff, who call themselves embodied cognitive scientists. And they say that actually concepts are not formal or mathematical, but that they are grounded in perceptual and other bodily capacities that are pre-conceptual. So perhaps Buddhists might find that very appealing, that ultimately concepts are not things in of themselves, but grounded in other things. So to give you an example, when we say somebody is the head of the monastery, now the head is of course a part of the body. So the cognitive linguists will claim that we use our idea of the body and where the head is relative to the body and map that onto an entity like the monastery and say that the head of the monastery is broadly to the monastery that the head of the body is to the body. right? So we use these bodily capacities to understand the world. And there's now very, very intensive work in trying to understand the bodily basis of several conceptual and other higher properties. What's interesting about it, like the previous version of computational studies of the mind, is that it's very, very precise. So to give you an example in English, I don't know how well it will translate into Tibetan. In English, we say, I saw the truth. And I can say, I was touched by the lecture. I feel close to you. So emotion is always handled in terms of distance metaphors, close, far, touch, right? And then sight is always about epistemic and other truth-bearing states. So it's not as if anything can be a metaphor for anything else. There seem to be specific, almost wiring diagrams that tell you that truth kind of states have to do with seeing, hearing has to do with obeying, touching has to do with feeling, and so on and so forth. So what this tells you is that potentially there is a sort of a bodily wiring diagram that tells you how our mind and its higher order concepts are sort of systematically wired according to certain lower order concepts or lower order experiences. And this is something, of course, very worth exploring. But that's where I think that the computational ideas, which you could argue were too rigid and formal, are making a comeback. And the reason is that the older idea of computation was the God's eye view of the world. If I can capture everything, all percepts, all language, all audition in one theory through one mode of representation, that would be a successful account. But biological beings don't live in that kind of God's eye view of the world. Instead, let me point out a very humble view of the world, which I call the moth's eye view of the world, right? The moth, the butterfly-like insect. So if you have a moth which is trying to find its mate, and you know moths can smell their mates from very, very far away with just a few smell molecules. But the task that the moth faces is a very, very hard task, because you have a few molecules. The atmosphere, as far as the moth goes, is very turbulent. And so what you have is sporadic stimuli that are scattered around, which are diffusing. So how does the moth infer the location of its mate from these kind of sporadic and local noisy stimuli? And that lends us to something which you might say is not the God's eye view of the world, but the uncertain reasoner, so the probabilistic view of the world, which is saying that really biological beings are trying to figure out where things are in the world out of noisy, dynamic, unstable stimuli. And if you can, all you need is to know what to do next. And as long as you do that well and the world supports, so it's like a rock climber. The rock climber wants to go to the top of the mountain, but all they need to figure out is where to put the next hand. And if you can keep grasping the next ledge, you're okay. Because broadly speaking, you're going up. So if you're broadly going up and you're grasping the next ledge and you get the right information to do that, you're all set. Right? And so that kind of local information theory, to me, is sort of where a great deal of intersection between the computational, the embodied, and the other approaches really lies, which brings me back to the original question that I raised. So where does this lead if you are a pramana theorist? Right? So what I believe is that the Indian philosophical systems are not formal systems. They always agree that mistakes and illusions are possible. So if that's the case, I believe that they should be capable of being given a probabilistic formulation. So the challenge that I would like to throw to the monks here is that can we give a mathematical formulation of the pramana theories in such a way that you should be able to say. So to a Nagarjuna-like critic, you should be able to say that my instrument, my pramas, are not certain. They cannot be 100% validated, but they are at least better than they were yesterday. And so as long as I'm improving, I have a reason to believe that I have a valid source of knowledge instead of an invalid source of knowledge. I'm all done. So to conclude, what I wanted to show you is that mathematics and the mathematical way of thinking is as useful in the study of the mind as it is in physics, and it offers an alternative approach which complements and learns from the more mechanistic approaches that people in the neurosciences use, but it also has a distinct place in the study of the mind. And I also believe that it has a lot of things to offer